We will discuss analysis of flat action today. The carding force gives us some indication about the opening action. The force is required to open the fiber tufts. The question that comes to the mind is how long the opening continues. Indirect evidence of the opening is by the carding force stress curve. So, in the diagram the carding force stress curve is shown. Now, what we see here is that the force continues to decline as we go from the very first flat to the last flat in the carding zone. Roughly there are 45 to 48 flats in the carding zone. So, here is the 45th flat and here is the first flat. So, the carding force was measured from flat location 1 to the last flat location, and the force stress curve is shown in the diagram. What we see here that there is a decline till 16th or 18th flat location, and thereafter the force remains more or less constant. So, if we divide the entire force stress curve into two zones, then we find the first zone is the opening zone, where the opening process continues, that the tufts get opened, and the next zone which starts from 16th or 18th flat location to the last flat is the cleaning zone. Here the cleaning process continues. The cleaning process how does the cleaning process happens? Now, beyond 16th flat locations, the flats are completely filled with fibers, they are fully loaded with fibers, and therefore, they are not in a position to really open out the tufts if at all they are left. So, these completely filled flats now acts as an absorbing medium, and they keep on absorbing the dust and trash particles being thrown by the cylinder during their entire journey over the carding area. So, we can say that first 16th or 18th flats, they actually participated in opening the fiber tufts, and the next set of flats are basically absorbing the dust, trash particles or naps being thrown away by the cylinder. So, the flats in a way are doing both the jobs, they are opening the tufts, fiber clusters, as well as they are absorbing the dust particles, trash, and thereby cleaning also. Now, what we find in the flat strip, there will some lot of long fibers in them. These long fibers are actually pushed into the flats at the very initial stage of opening, whereas when the tufts are approaching the carding zone, that time all long and short fibers, everything is pushed into the flats. There is no discrimination in terms of selecting the fibers. So, initially whatever is pushed into the flats, some of those remains there, and therefore, quite a few long fibers are pushed into the flats and they remain there. However, in the latter part of the journey of the same flat, it no more absorb any long fibers, but it keeps on absorbing the short fibers, trash particles and naps as already been told. Hence, we find that by the time the flats move out of the carding zone, if we analyze the flat strip, we will find that though majority of the fibers are short in nature, there are some fibers which are long also, and these long fibers were pushed into them when the same flat was occupying the first flat location in the carding area. If we increase the cylinder speed, there will be more centrifugal force which will be acting on the trash particles, on the dust particles and all other impurities which are there, and therefore, one can expect that the cleaning to improve as we increase the cylinder speed. However, too high a cylinder speed may lead to short fiber generations, because there is every chance of fiber breakage as well. Hence, very high cylinder speed needs to be avoided. So, whatever speed we have to keep, that will depend upon the type of fiber and the strength of the fiber that we are going to process. Accumulation of flat strip. This has been studied. The way the flat strip accumulates in a given flat is shown in this diagram. What we see here, and on the x axis we have time, and in the y axis there is flat strip depositions, which is in gram. So, what we see here, for the first flat location, the flat strip deposition increases with time and it gradually levels off. It is also being shown for the 30th flat locations. So, the rate of deposition in the last flat is slow and then it also levels off. Now, this study was done on a machine where the flats are not really moving, but they are actually stationary, and still it gives us a lot of information about the way the flats get loaded with fibers as a function of time. If we look at this graph and plot log of s with log of time, then we get a straight line as shown in the lower diagram. And the empirical equation that we can fit is that log of s equal to alpha plus beta log t, or we can write s is equal to alpha t to the power beta, where s is the weight of flat strip, alpha and beta are the constant and t is the time. This diagram gives us information about the type of fibers and trash deposition in a given flat. Here is a plot where on the x axis we have running time log t, and on the y axis we have weight of flat strips, and we also have a log value of the weight. Now, here the diagram is clearly showing to us that as a function of trash keeps on increasing, short fibers shown by the red line also keeps on increasing, the long fibers also increases, and the sum of all these three, total flat strip, also increases with time. The slopes are different. The slope for the trash particles is very high, then the rate of deposition of trash is much faster in comparison to the short fibers shown by the red line. Its slope is less in comparison to the trash, and the slope for the long fiber is still less, and therefore, we can say the deposition rate of long fibers will be less in comparison to short fibers or trash particles. This is how the deposition takes place. Rate of trash deposition is constant, that is weight of trash is proportional to the running time, and flats irrespective of the weight of deposited fiber and trash continues to absorb trash particles. This is what has been shown by some researchers. Now, this is also interesting point, that in which direction the flats should move in a carding machines. The flats, as we all know, they move very slowly with respect to the cylinder. It practically appears to be constant. Now, the question that comes to our mind is in which direction the flat should move. From the carding point of view, what we need is relative motion between the cylinder and the flat, and the relative motion could be there if the flats move slowly in the forward directions, or if it remains stationary, or if it moves in the backward directions. In all the cases there would be relative motions, and hence carding is actually possible. However, the machines that have been developed, there are two ways in which the flats can move, and we will study these two. One is they can move in the forward directions, which is there in the most of the carding machines. They can also move in the backward directions. Now, the forward movement of flat, what are the advantages? If the flats move forward directions, the cylinder will assist in moving the flats, but providing part of the drive to the carding force. That is one of the advantage we get, and the removal of flat strip becomes easier due to downward inclination of the flat wire points at the front of the card. So, when the loaded flat, loaded with short fibers, trash particles and other fibers, they reach the front end of the machine, now we are supposed to clean them, so that the clean flats can be fed back to the carding machine again for carding actions, because all the flats are actually connected together in the form of a chain, and hence the direction of inclinations of the wire point of the flats at the front of the machines, and if we use a brush or some other combing device to remove the fibers from the flats, then the inclination of the wire points will help in easy removal of the flat strip, and therefore, forward motion in a way is advantageous. The disadvantageous points are larger size trash particles liberated through carding action and absorbed into the first few flats are crushed into the smaller pieces, as these flats remain in the carding zone for a long period of time. These crushed particles re-enter the carded stock and thus affect cleaning. What happens is that some of the bigger trash particles which get pushed into the flats right at the beginning of the carding zone, some of the big particles may get crushed as the flats move throughout the carding zone, and therefore, these smaller pieces of the trash particles will remain, and they can re-enter the fibers, and as the size becomes smaller and smaller, removal of these finer trash particles becomes more and more difficult. So, that is the disadvantage, because the particles, the bigger size trash particles spend lot of time in the carding zone, because they have to move from the first pad location to the last pad location. It could be 46th or 48th flat. In comparison to this, let us see the backward movement of the flat. What would happen if we make the flats to move in the backward directions? From the carding point of view, there will not be any problem, carding action will still be there. Now, this time the cleaner flats will be introduced from the Dhafir side. So, from the front of the machine, the flats will be introduced and they will move backward, though the flat fiber absorbing capacity reduces by the time they reach the beginning of the carding zone, sufficient still remains to eliminate the dirt. That is, when the flat reaches from the back end to the front end to the back end of the machine, where the carding zone starts, the flats will be already loaded with fibers, and therefore, their opening capability one might expect to be much less, because these flats are already loaded with some fibers. They had to travel from front part of the machine to the back part of the machines, and during this journey they absorb lot of fibers. So, by the time they are approaching the entry point of the carding zone, they are already full with fibers, and therefore, one can expect the carding action to be less efficient in nature, but still some carding is still possible. The larger size impurities are not transported through the whole of the carding zone, but removed immediately. That is the biggest advantage that we get, that the bigger trash particles which are coming from the liquor inside and they are encountering the very fast flat in the carding zone. These trash particles, once they get lodged into the flat, they will be moving out from the carding zone in this case, and therefore, these bigger size particles will not have the opportunity to move throughout the carding zone, and therefore, possibilities of getting crushed will be less and less. These are the advantages of the backward movement. This diagram on the right hand side shows the dot takeoff versus the flat location. We see that first few players will take up more dots, and as we go along the flat locations, that is, I go towards the front end of the machine, the dot takeoff will be less and less. So, this is all about the way the flats are actually working. So, what we can say or we can conclude is that carding action is possible when we have both flats and cylinders along with their work points inclined in the right directions. The flats open or teased out the fiber tufts. At the same time, they also act as an absorbing medium for the dust particles and short fibers and nets and any other trash particles which could be there. So, they are playing a dual role, they are opening out the tufts, they are separating out the fibers, at the same time they are also acting as a absorbing medium. And hence, even though we can see that we could finish the opening action by having 16 or 18 flats, still we keep 48 to 50 flats in the carding zone, because the rest of the 30 flats that we keep it on the carding zone are supposed to act as an absorbing medium, and therefore, participate in only cleaning part of the fiber stock. The next point that we are going to discuss is analysis of forces acting on the fiber on a cylinder. There are so many fibers on the cylinder. Let us look at an isolated fiber held by the cylinder wire point. So, in the diagram we see there is cylinder surface, there is one cylinder wire point or one pin, whatever you say. The black line indicates a single fiber and the cylinder surface is moving forward. What we can say here is that these fibers, as it moves forward, because it is attached to the cylinder wire point, the forces which are acting on it. First is the force T, which is the centrifugal force acting because the cylinder is rotating. The other force which will be acting on it is the force P, that is the air drag acting parallel to the clothing base. So, T is one force and P is another force. Beta in this case is the inclination angle of the wire point with respect to the cylinder surface. We can resolve T into two components, Q and H, or Q is T sin beta, this is Q, which is equal to T sin beta, and the other one is H. If you look at the H is here and H is T cos beta. Similarly, P also can be resolved into two components, one is Q capital Q, which is P cos beta, and other one is capital H is P sin beta. Therefore, what we can see here that the forces small h and capital H is acting perpendicular to the wire point, whereas the force capital F and capital Q is trying to push the fibers towards the base of the wire point. The force small q is trying to take away the fiber from the wire points. So, these are the various forces which are acting on the wire point, and the perpendicular forces gives rise to frictional resistance. So, the frictional force which is acting on the fiber is F, and F is mu into H plus small h. So, N is equal to the normal force is capital H plus small h, and if mu is the coefficient of friction between the metallic wire point and the fiber. Therefore, the frictional force which is acting on the fiber, which is F equal mu into capital H plus small h. The equilibrium equation is given by equation number 1, which shows that capital N is basically H plus small h, and H is P sin beta and small h is R cos beta, and therefore, small q is also capital Q plus F, and we have already seen small q is equal to T sin beta, capital Q is equal to P cos beta, and F is the frictional force which is mu into N, and therefore, this is equal to mu into P sin beta and T cos beta. We are basically replacing this here. The fiber can move towards the tip of the wire point if T sin beta overcomes P cos beta plus mu into this. In this conditions, the fiber will move towards the tip, and eventually it may move out of the wire point. This inequality equations, if we simplify it, we can write capital T into sin beta minus cos beta is should be greater than this, and from there if we go to the next page, we can write T by P, this ratio has to be greater than this function of the angle of the wire point with respect to the base and the value mu, coefficient of friction. Therefore, fiber will try to move away from the wire point if T by P is greater than this value. The fiber movement along the wire point tip resulting shading depends upon the angle beta and angle mu. We can take a typical case, suppose mu is 0.23, condition of shading for various values of beta are stated in this case. When T by P is greater than 0.93 for beta equal to 60 degree, T by P value has to be more than 0.75 when beta is 66 degree, and T by P value should be greater than 0.66 for beta equal to 70 degree. For 3 different values of the base angle, we are showing the what should be the T by P value, so that if it overcomes the value stated here, then the fiber will move towards the tip and finally, it can shade off. If we keep a fixed value of beta and change the friction for 3 different frictions, the corresponding data of T by P is given. So, as we increase the friction from 0.2 to 0.26, the conditions of shading will be that T by P has to be more than 0.8. Therefore, the condition of the fiber shading becomes favorable at larger value of beta and at smaller value of mu, and hence we can see that in order to ensure that carding action continues and the fibers, instead of going away from the wire point, they should move towards the base. So that they are retained by the wide points of the cylinder and hence participate in teasing actions. So, they are subjected to teasing by the wide points of cylinder and Dhafir. So, therefore, the angle of the wide points has to be always less than 90 degree. This equation we can further move forward. The centrifugal force we can write T is G V square V c square G into capital R, where G is the weight of the fiber, G is the acceleration due to gravity, V c is the surface speed of the cylinder and R is the radius. Therefore, this is what T would be, and weight of the fiber we can write is the volume of the fiber multiplied by the density. So, pi d square by 4 into L is the volume of the fiber and gamma is the density, we get the weight. So, therefore, you can write T is basically this, just substitution of the value of G in equation 4. From there, now we can find out what is the value of P, the air drag force on the fiber. The air drag force can be stated by this formula, that is, it is half C A rho V relative square, where C is the drag coefficient, rho is the density of air, A is the largest projected cross sectional area of the fiber in the direction of the airflow, V relative is the relative velocity of the airflow. So, V real is V c minus V absolute, or V ab is the absolute velocity of the air at the plane of the fiber. So, if we write these two values in the previous equations, we get T by P as stated in equation 8, that is T by P is equal to pi d square L gamma V c square 2 small g capital R capital C A gamma V relative. Now, from here if we study this equation carefully, then we can make certain conclusions, that the chance of fibers being thrown away from the wire point increases as T by P increase. And when it will increase? If we increase the cylinder speed, because cylinder speed comes in the numerator, if we increase the fiber diameter, that is, if I go for heavier linear fibers or if I go for higher density fibers, then chances of fibers being thrown away will be more. Or if I reduce the cylinder radius or relative air velocity. So, this is how the various parameters are acting and deciding the possibilities of a fiber being thrown away from the cylinder or not. We can now say that short fibers situated close to the cylinder surface is more likely to be shed, since V real is small in this zone. So, any short fibers very close to the cylinder surface is most likely to be thrown away, or they are likely to be shed, since V relative velocity is less for them. A long fiber situated in a zone remote from the cylinder surface is less likely to be thrown off, since V relative velocity is high here. The layer of fiber very adjacent to the base of the wire point is moving almost at the speed of the cylinder surface. The air layer which is nearer to the tip of the wire point will be moving at a little lesser speed, and that is why these differences are expected. From there, now we take up another aspects of the carding machines, that is the cylinder Dhafir region of the carding machines. Once the flats end, the zone between the flat and the Dhafir, that is this zone, needs to be protected so that the fibers are not thrown away from the machine or they should not escape the machines. So, this zone is surrounded by 3 plates in the old version of the carding machines. We call them top plate, middle plate and bottom plate. Top plate or the upper plate is known as percentage plate, since its setting with respect to cylinder surface decides the amount of flat strip waste. So, how much flat strip will be generated, to some extent it can be regulated by the setting of the top plate with respect to the cylinder surface. The purpose of the middle plate is that it can be opened any time to assess the sharpness of the wire point and whether we need any grinding or not. So, this is for more for inspection purpose. So, the middle plate is therefore mounted on a bracket with cast iron hinges and is acts like a door. So, that any time we can open it, and if we want to inspect the condition of the wire points on the cylinder, we can inspect it. And when you need to grind the wire points in order to increase their sharpness, then also here is a zone which is accessible to the grinder, and we can make the wire points very sharp whenever we need it. The bottom plate is simply acts as a cover to the cylinder, it has no other purpose. So, what we see that the cylinder actually is surrounded from all sides by flats, back and front plate, Dhafir, Likarin, undercasing, which is here, is not shown here, the undercasing could be here, and therefore, the air existing between the cylinder and the surrounding parts moves along with the rotation of the cylinder. We have already discussed this earlier, that as the cylinder rotates, the layer of air which is adjacent to the cylinder also rotates along with it. This rotation of the air current has its own role to play. We will see that on the front top plate and its influence on flat strip, as we have stated earlier, that the setting between the front top plate and the cylinder affects the amount of flat strip. Question comes ki what are the reasons for this? There are 2 theories to explain this phenomena, one based on pneumatic actions or air current, and the other one is based on the mechanical actions. We will look at them. Now, here we will first study the airflow mechanism. Here in the diagram we see that the front top plate is shown along with the flats. The flats are linked together in the form of a chain, but there are always some gaps between the flats, and through these gaps the air can always enter or they can also escape. The front plate is positioned in such a way that there is an increasing gap between the cylinder and the plate from top to the bottom. That is, the gap here between the plate and the cylinder is little less than the gap which is there at the other edge of the front plate. So, the front plate, top front plate, this is the forward edge, this is the backward edge. The gap here little less, the gap here little more. Now, what is the effect of this? According to Bernoulli's theorem, P plus half rho v square will be always constant, considering the effect of gravity to be negligible. Here P is the air pressure, rho is the density of air, and v is the velocity of air. Since the volume of air flow remains constant, the velocity of the air at the edge A, that is here, will increase, causing pressure drop at the edge A. So, the volume of the air current remains constant. Here the gap is low, there the gap is more, here the velocity will increase. As a result, the pressure drop will be there. Because of the pressure drop, what will happen? Air will try to enter, it will try to enter from the top part of this front plate edge from this side, it will also try to enter in between the gaps of the flats. Now, what happens because of this? A closer setting will increase the velocity and hence reduce the pressure more at this point, enhancing the velocity of incoming air from the surroundings. This will cause lot of fibers breached between the flats to be pushed downwards and caught by the cylinder rod points and will be carried forward. That is, if I go back, that since there is a drop of pressure here, air will enter from this side and whatever fibers are breaching between the flats, see the spaces between the flats will be connected by some fibers, we call them breach fibers. Now, all these breach fibers will be pushed downwards because of the incoming air current. As soon as they push downwards, they will be caught by the rod points of the cylinder and therefore, they will be physically entrapped by the cylinder rod points and hence they will move forward along with the cylinder. So, therefore, pressure drop here will cause air to gush in, the breach fibers will move downwards because of the pressure of the air or the velocity of the air, they will be caught by the rod points of the cylinder and cylinder will take these fibers and hence the proportion of fibers in the flats will go down, therefore, flat strip will reduce in quantity. That is how the airflow mechanism is going to work. Now, we will discuss the mechanical action. Now, here is a diagram where this is the cylinder moving in these directions and these are the rod points. On the top we have the flat along with the rod points. At the exit end of the carding zone, some fibers, especially the longer ones, approach the top edge of the front plate. Here is this is the front plate. So, some long fibers will approach at the exit end the front plate with both the ends caught by the flat and the cylinder rod point. Like here is a fiber where this end is caught by the flat rod points and this end is caught by the cylinder rod points, and the middle of the fiber is now caught by the edge of the front plate. Now, this is the situation which will happen to many long fibers. As the cylinder will move forward, tension will develop in this fiber. When the tension develops, now what will happen to the fiber? Who will take away the fiber? It all depends which wire point exercises more grip on the fiber. Whether the grip of the cylinder rod points on the fiber is more than the grip of the flat rod points. It all depends upon this, and the gripping power in a way depends upon the inclination angle that the fiber makes with respect to the rod points. That is, that depends upon this angle alpha shown here or the angle beta shown in this diagram. When the plate is set close to the cylinder surface, the angle alpha reduces in comparison to what is obtained at the wider setting. So, two cases are shown here. In one case, the dotted line shows the situation when the front plate is away from the cylinder surface, and the firm line shows situation when the front plate is closer to the cylinder surface. And if we look at the diagram carefully, then we will see that the angle that the fiber makes with respect to the wire point is angle alpha and angle beta. Then we will see that when the setting is closer, alpha n is less than alpha w, where alpha n is the angle in the normal situations and alpha w is the angle when the setting is wide. So, alpha is the angle that the wire point makes with the cylinder, and beta is the angle the fiber makes with the flat. So, in the case of closed setting, this is the situation, alpha n will be less than alpha w and beta n will be less than beta w. Therefore, P cos alpha will be increasing and P cos beta will be decreasing, where P indicates the tension on the fiber. Hence, with closer setting, the grip of the cylinder on the fiber becomes firmer and that of the flat becomes weaker. So, I must write that P is the tension on fiber, and P has been resolved in the P cos alpha. Similarly, there P has been resolved in the P cos beta. So, the closure setting P cos alpha, if you look at the value of alpha, it is less than beta, and hence P cos alpha will be more and P cos beta will be less and less, and therefore, the grip of the cylinder rod points on the fiber will be more in comparison to the grip of the flat rod points. So, what will happen? The fibers will mostly go along with the cylinder, and therefore, flat strip will reduce with the closer front plate setting. So, this theory is based on the mechanical actions. There is no role that the air current is going to play here, and the previous theory is based on solely on the air current that is generated by the cylinder. The next discussion topic is the cylinder Dhafir region. As I said earlier, that this zone, in the case of traditional card, we have 3 plates placed one after the other. In the case of modern card, there is an additional thing over here, and what are these? The middle plate is replaced by a suction hood and post carding segments to suck out the dust laden air within the card generated by the vigorous carding actions. See, in the modern card, the production rate has increased. So, rate of generation of dust has also increased. So, you have to exploit each and every opportunity in terms of sucking out the dust laden air. At the same time, because the productivity is more, we have to find out opportunities to open out the tufts or the cluster of fibers wherever possible. So, in this zone, when the plates are there is no opening actions. So, in the high production cards or modern cards, since opening by the flats may not be sufficient, so part of this zone starting from flat to Dhafir is used to do 2 things. One, we have placed there post carding segments where we have some wire points, and therefore, some kind of carding action is taking place between the post carding segments and the cylinder wire points. So, that in case any tufts are accidentally left unopened, by the flats and cylinder actions due to heavy production rate, there is a large opportunity for those tops to get opened out before they land onto the Dhafir. And since we generate lot of dust, especially in the case of cotton, so therefore, there are suction slots also, so that the dust laden air that is generated because of the vigorous or intensive carding action between the cylinder and the flat, some of those dust particles can be sucked out by having a suction here. This is the suction point. So, this is the purpose that the zone from flat to Dhafir is used to suck out the dust particle as well as to open out the fiber tufts. Now, we go to the under casing of the cylinder, that is the zone which is left now. Now, here is a diagram showing the under casing. In the traditional card, there are two sheets, a sheet from here to there and another sheet from here to there. The under casing was divided into two parts, one part towards the Dhafir, the other parts is 1 and 2, 1 is towards the Licarin, 2 is towards the Dhafir. This was there in the traditional cards, and the purpose of this under casing was to give support to the fibers, so that they do not fall easily from the cylinder surface and accumulate below the cylinder. At the same time, the openings were there, through those openings some trash particle will fall down, and hence slotted sheets are used or grid bars are used. So, that you have openings which will allow the some heavy trash particles to fall down. At the same time, it will also give support to the fibers which are still held by the cylinders and have a possibility to be thrown out due to the centrifugal force. That is how this was, but it was found that the slots or grids which were there, they will result in powerful vortices if we increase the cylinder speed. And therefore, like here we used to get vortex, here used to get vortex. So, this air current here used to get disturbed because of these slots which are there, because you have some portions which are open, there are some portions which are solid, and when the air is passing over it, somehow they used to create vortex, and these vortex will disturb the arrangement of fibers on the cylinder. At the same time, they may not allow all the trash particles to fall down. This was seen when slotted under casings are used, but with traditional card this used to work fine. With modern card, high production card, difficulty was there, and therefore, the little differences were made. With the modern card, we have slotted sheet was replaced by a closed sheet with suction hood to avoid creation of small air vortices, and this will eliminate the possibility of fiber loss due to high centrifugal force. So, you see that now there is no slot which is there, it is a sheet, but only what we have is suction slot here, 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 these are all suction slot. Through this suction slot we will be able to suck out the dust laden air. However, the fiber loss will not be there. That is the advantage of the under casing that we have with modern cards. and that is the end of today's lecture. Thank you.